So the integral test is suppose that a sub n is a sequence of positive terms and a sub n is equal to a function of n where f is continuous, positive decreasing function of x for all x greater than or equal to capital N where capital N is a positive integer. So if the integral from capital N to infinity of f of x dx converges, then the series a sub n will also converge. And if the integral from capital N to infinity of f of x diverges, then the series of a sub n also diverges. So for our first example, we're going to do the integral test. So we'll look at the integral from 1 to infinity. 1 because the value of capital N is equal to 1. And then the a sub n is 1 over 1 plus 10n. So we'll integrate 1 over 1 plus 10x dx. This is an improper integral, so we have the limit as a approaches infinity of the integral from 1 to a of 1 over 1 plus 10x dx. Then by u substitution, u is equal to 1 plus 10x, du dx is equal to 10, du over 10 is equal to dx, and u of 1 is 11, u of a is 1 plus 10a. So we have the limit as a approaches infinity of the integral from 11 to 1 plus 10a of 1 over u du over 10, which is equal to the limit as a approaches infinity of 1 over 10 natural log of the absolute value of u from 11 to 1 plus 10a. Replacing in those values following the fundamental theorem of calculus, we have the limit as a approaches infinity of 1 over 10 natural log of 1 plus 10a minus the natural log of 11. And as n goes to infinity, this limit goes to infinity, so that diverges. So since the integral diverges, then the series will also diverge. The second example will also conduct the integral test. So the n value is equal to 1. The a sub n is equal to 1 over n cubed, so we're looking at the integral from 1 to infinity of 1 over x cubed dx. Since it's an improper integral, we're looking at the limit as a approaches infinity, integral from 1 to a of x to the negative 3 dx. By anti-deriving, we have the limit as a approaches infinity of negative 1/2 x to the negative 2 from 1 to a. Following the fundamental theorem of calculus, we have the limit as a goes to infinity of negative 1 over 2a squared minus negative 1/2. Calculating the limit to get 0 plus 1/2, which is equal to 1/2. Since the integral converges, then the series also converges. So the next test is the p-series test. So if you have a series that's 1 over n to the p and p is greater than 1, then the series converges. You can see the previous example number 2 of how that works. Then if p is between 0 and 1, then the series diverges. So we look at a series from n is equal to 1 to infinity of 1 over the square root of n. That's the series of n to the negative 1/2. So by the integral test, we can take a look at the integral from 1 to infinity of x to the negative 1/2 dx, which is the limit as a approaches infinity of the integral from 1 to a. Anti-deriving, we get 2x to the 1/2 from 1 to a. Following the fundamental theorem of calculus, that's the limit as a goes to infinity of 2 square root of a minus 2, which is infinity. So the integral diverges, which means that series would diverge. And then if p is equal to 1, the series also diverges. So for example, if we have p is equal to 1, we're looking at the series 1 over n. Then by the integral test, anti-deriving from 1 to infinity of 1 over x dx, which is the limit as a approaches infinity of the integral from 1 to a of 1 over x dx. Anti-deriving to get to the limit as a approaches infinity of the natural log of the absolute value of x from 1 to a. Replacing in the value of a and 1, we have the limit as a approaches infinity of the natural log of a minus 0, which becomes infinity, so that also diverges. So the first example, using the p-series test for this series, rewriting the series as n is equal to 1 to infinity of 1 over n squared. The p-value is 2, which is greater than 1, so then the series converges. In the next example, again using the p-series test, the value of p is equal to 1, so then the series diverges.